what you have learned so far in quantum mechanics is Heisenberg's approach to quantum mechanics, which essentially involved matrices to represent dynamical quantities, and the equation of motion was same as classical equation, and the quantum condition was represented as Px minus Xp equals H cross over I, the identity matrix I. We have also learned another approach, which is Schrodinger's approach, which is very different on the surface from Heisenberg's approach. And what happens in this approach is the particle has a wave function psi x associated with it, number 2, there is a wave equation known as the Schrodinger equation, and 3, the eigenvalues determined by the boundary condition give the energies. So, these two are very different approaches, but what you learnt is that for simple harmonic oscillator both gave the same answers. Is it mere coincidence that both give the same answer, or is there a deeper meaning? Is there a connection, or are these two approaches the same? They are just represented in a different way. What we are going to do in the next 2 lectures is learn that actually Heisenberg's approach to quantum mechanics and Schrodinger's approach to quantum mechanics are one and the same thing. And this will also teach us about how quantities are represented in Schrodinger's approach. For example, we will write the operators for the momentum and so on, and all that requires a little bit of mathematical preparation, which I am going to do in this lecture. So, this lecture is essentially devoted to some mathematical aspects related to the solutions of the Schrodinger equation. So, first thing that I want to talk about is the ortho normality of wave functions. Let me explain. Normality is a property that we enforce. Ortho means perpendicular. So, this first I am going to talk about the ortho behavior, the perpendicular behavior of two wave functions. So, what we mean by that is, if there is a wave function psi m x, and I am going to restrict myself to one dimension. The idea is to give you the concepts. One dimension makes it easy. Psi m star psi x product, where m and n are 2 indices for the energy level, integrated over is equal to 0 if m is not equal to n. So, this is what I am going to call the orthogonal property of wave function. I am going to explain in a bit what we mean when we say m is not equal to n. What it would amount to is that if the energy related to mth level is not equal to energy related to nth level. So, this is the orthogonal property of wave function which is going to be satisfied. Normal means, and that I will explain the second point, normal means that for the same n, psi n star x, psi n x dx, which is equal to integral of mod of psi x square dx is going to be 1. We choose the constant, we choose the constant in front of psi n such that it is integrated to 1, and the integration is carried all over the space minus infinity to infinity. Similarly, in orthogonal behavior also is from minus infinity to infinity. So, normal part I will come to. Normality we enforce, orthogonality, that these wave functions are orthogonal in the sense of the way I have explained above, it follows. So, let us prove that. So, to prove this, let us take the Schrodinger equation d2 psi m by dx square plus Vx psi m is equal to E m psi m x. If I take its complex conjugate, all the real quantities remain the same, psi square over 2 m d2 psi m star over dx square plus V is real, psi m x star is same as E is real, psi m star x. So, we have just written Schrodinger equation for psi m for its complex conjugate as well as the wave function itself. So, now I am going to prove that if what we have to prove now, if E m is not equal to E n, then integration psi m star x psi n x dx is equal to 0. So, let us write the equation for nth level, which is minus h cross square over 2 m d2 psi n over dx square plus Vx psi n x is equal to E n psi n x multiply by psi m star x from the left and integrate over dx. This is the operation I am carrying out. So, that this equation can be written as minus h cross square over 2 m integration minus infinity to infinity psi m star x d2 psi n x over dx square plus integration psi m star x Vx psi n x equals E n integration psi m star x psi n x dx. All integrations are from minus infinity to infinity. So, that is equation number 1. Let me simplify the first term, this term, which I can write as minus h cross square over 2 m integration minus infinity to infinity d by dx of psi m star d psi n by dx plus h cross square is integrated over x over 2 m integration d psi m star over dx d psi n over dx dx. The first term can be integrated fully, and since psi and their derivatives all go to 0 as x tends to infinity, this term is going to be 0, and therefore, the first term can be written only as plus h cross square over 2 m integration from minus infinity to infinity d psi m star dx d psi n dx dx. and therefore, I can write the Schrodinger equation after this integration as h cross square over 2 m integration minus infinity to infinity d psi m star over dx d psi n over dx integrated over plus minus infinity to infinity psi m star x v x psi n x dx equals E n psi m star minus infinity to infinity psi n dx. Let me now write the equation for psi m star d 2 psi m star dx plus v x psi m star x equals E m psi m star x. This I had written earlier. Now, what I am going to do is multiply it from the right side by psi n x and integrate minus infinity to infinity dx. So that this equation now becomes minus h cross square over 2 m integration minus infinity to infinity d psi m star over dx square psi n x dx plus integration minus infinity to infinity psi m star x v x psi n x dx equals E m integration minus infinity to infinity psi m star psi n dx. I can again show by the same trick as I did earlier that this term is equal to plus h cross square over 2 m integration minus infinity to infinity d psi m star over dx d psi n over dx dx. You do exactly the same thing, you take one d by dx out and then expand this. So, I have got these two equations, let me number them. Number 1 is this one that I wrote on top, and number 2 is this equation. So, I have h cross square over 2 m integration minus infinity to infinity d psi m star dx d psi n over dx integrated plus integration minus infinity to infinity psi m star x v x psi n x equals E n integration minus infinity to infinity psi m x psi n x dx. This is my equation number 1. And equation number 2 is h cross square over 2 m integration minus infinity to infinity d psi m star over dx d psi n over dx integrated over x plus minus infinity to infinity psi m star x v x psi n x dx is equal to E m integration minus infinity to infinity psi m star, there should be a star on top also, there is a dx psi n dx. This is my equation number 2. Subtract 2 from 1, and when you subtract, you notice that the first term cancels. So does the second term. So, what you are left with is 0 on the left hand side is equal to E n minus E m integration minus infinity to infinity psi m star psi n dx. And now you can write if E m is not equal to E n, which implies E n minus E m is not equal to 0, it immediately means that integration minus infinity to infinity psi m star psi n dx is 0. Therefore, we prove the first property, the orthogonality of the wave functions. That is one thing we will require later, and this is always going to be true in case of Schrodinger equation, because we require nothing, just the solution of the Schrodinger equation, that two eigenfunctions whose eigenvalues are different they are orthogonal. Number 2, this is a property we are going to enforce, is normality, and this will have significance later when I discuss bond interpretation. And normality is going to be, so we have already seen that psi m star psi n dx is 0 for E m not equal to E n, and we are going to enforce that integration for the same index mod square dx be equal to 1. Suppose it is not 1, suppose, so let us write, suppose integration psi n square dx is equal to some number c, then I can always define a new psi n x which is equal to the old, let me write this, old psi n x divided by square root of c, so that this condition of normality is going to be enforced, because I can always multiply a solution of differential equation by a constant. So, I can redefine it. So, normality is enforced, and therefore, in general I am going to write that psi m star x psi n x dx is equal to delta m n, where delta m n is the Schrodinger delta. So, on the side I will just write that delta m n is equal to 0 if m is not equal to n and is equal to 1 if m equals n. So, we have 1, discuss the property of orthogonality, number 2, a convention that we are going to enforce normality on the wave functions, and third, which I will require again, is completeness of wave functions. This is the third property, and that is when I write the Schrodinger equation minus h cross square over 2 m d2 psi n over dx square plus V x psi n x equals E n psi n x, then the set psi n, where n runs from 1, 2 all the way up to infinity, is complete. I am not proving it, so you can say I am assuming it. What it means is that any completeness, any function, general function satisfying the same, and that is emphasized, same boundary conditions as this set psi n can be expanded in terms of psi n as f x equals summation c n psi n x. And if you recall from your mathematics, this is similar to a Fourier series, where we assume, and maybe you have heard this term earlier, that the sine function, cosine function and exponential functions, they form a complete set for those periodic functions. So, here, so there the boundary condition is periodicity, here the boundary condition satisfied is that satisfied by psi n. For example, so let us take an example, would be, let us say, particle in a box. So, in the particle in a box, if you recall, wave function is this function, second one is like this, third one is like this, and so on. And we assume that this forms a complete set, and therefore, any function, some arbitrary function which vanishes at the boundaries x equals 0 and x equals L, this is some f x, can be written as f x equals integration C n. Recall these functions are n pi over L x, because they satisfy the boundary condition and these C n's can be determined. So, this means that this forms a complete set. Now, it is, as I said, convention is to normalize the wave functions. So, the sin n x is not normalized, because let us see what is this integration. If I integrate from 0 to L sin square n pi over L x dx, this comes out to be L by 2. And therefore, to normalize it, I have to write, so normalized particle in a box wave function would be sin n pi over L x divided by square root of L by 2, which is square root of 2 over L sin n pi over L x. And what then orthonormality is, that integration 2 by L sin m pi over L x sin of n pi over L x dx is equal to delta m n. So, that when m equals n, it is 1, when m is not equal to n, it is 0, which you can check yourself. And the claim is for completeness that f x that satisfies the same boundary condition can be written as C n times this normalized wave function. Let me write this as phi n x, where phi n is equal to square root of 2 over L sin of n pi over L x. How do we determine C n? I will multiply f x by phi m star x dx, integrate from minus infinity to infinity, which in this case becomes 0 to L, which is equal to summation n C n phi m star x phi n x dx minus infinity to infinity, and by orthonormality this becomes summation over n C n delta m n, and this equals C m. So, we have also determined C m. That means f x is equal to summation C n phi n x, where C n is nothing but integration of f x phi n star x dx. That is what completeness means. Now, I am going to write completeness in a different form, and that is useful later. Writing completeness in terms of Dirac delta function. So, what we have just said is that an f x is equal to summation n C n phi n x, where C n is equal to integration minus infinity to infinity f x, and let me write this f x prime phi n star x prime dx prime, because x prime is a dummy variable, x I am using earlier. So, I do not want to use that again, and then I have f x is equal to summation over n integration minus infinity to infinity f x prime phi n x prime star dx prime times phi n x. I can rearrange terms and write this as integration minus infinity to infinity dx prime f x prime, and then take the sum inside, because that acts only on phi n star and phi n x prime phi n x summed over n. This is what completeness has given us. Now, I also know that f x is equal to minus infinity to infinity dx prime f x prime delta of x minus x prime, and this immediately tells me, these two things together tell me that summation n phi n star x prime phi n x is equal to delta of x minus x prime, which I also can write as, switch the indices, summation n phi n star x phi n x prime is one and the same thing, because delta function, it does not matter if I change x and x prime indices. So, this is another way of expressing completeness. So, let me conclude this lecture, Introduction to Mathematics, by writing number 1, psi n form an ortho normal set of functions, and what that means is integration psi m star x psi n x dx is equal to delta m n, and the other property that psi n normalized form a complete set, and that means summation psi n star x psi n x prime is equal to delta x minus x prime. In the next lecture, I will use these properties to show the equivalence of Heisenberg's and Schrodinger's approaches to quantum mechanics.